Hi folks, we're going to take a look at number 17 on page 180. So here what they tell us that f and g are both positive numbers, and they tell us that f has a local max at c, g has a local min at c, and they want us to show that the function given by the quotient of the two functions also has a local max at x equals c. Okay, so with one of these functions, the first thing that I think one should do is figure out what it is we need to show. So what needs to occur in order for this function to have a local max at c? So we know that from Fermat's theorem that the only place to even look for local extrema are at critical points. Okay, so here we know that the first thing we have to show is that h prime at c is either equal to 0 or does not exist. Okay, because that's where our critical points are going to occur. And the second thing we have to show is that in order for it to be a local max, the derivative function has to go from positive to negative. So it has to go from increasing to decreasing in order for there to be a local max. Okay, so this is what we need to show. So let's figure out what they've told us. So we already know that f and g are positive. They've told us that f has a local max at c. Okay, so what does that tell us about f? It tells us that f prime at c is equal to 0 or does not exist. As before, the only place to have a local max or min is at a critical point. And the other thing that has to happen is f at prime has to go from positive to negative. So if I take, my number line and c, and this is for f prime, I know that f prime has to go from positive to negative. So if I let a represent some number smaller than c, the derivative there has to be positive. And if I take b as representing some number slightly greater than c, that number has to have a derivative that's negative. Okay, and similarly, but slightly different for g. Okay, so g again, g prime at c has to be equal to 0 or has to not exist. Okay, and if we think about how the derivative of g behaves in the neighborhood of c, it has to go from negative to positive. So if I pick my number a, that same number a slightly to the left of c, derivative has to be negative, and if I pick b just to the right of c, that derivative has to be positive. Okay, so this is what we have at our disposal, along with the fact that f and g are positive. Let's see if we can prove these two conditions so as to show that h does in fact have a local maximum at c. So we have to determine whether h prime at c is equal to 0 does not exist. So let's start by finding h prime at x. Okay, so here, in order to find h prime at x, of course, we're going to have to use the quotient rule. So that's just given by the derivative of the numerator times the denominator function, okay, minus the numerator function times the derivative of the denominator function, all over the square of the denominator function. Okay, so now let's see what's happening with h prime at c. Now, the only thing I'm going to work with here, because you see, I don't have any information about any values of this function or its derivative, but I do have information about the sign of the function. Okay, so let's assume that the derivative exists here. I'll deal with the possibility of the derivative not existing in the second part. Okay, so let's assume that f has its local maximum at c and that the derivative is equal to 0 there. That means that f prime at c is equal to 0, and g at c, well, we know is just some positive number. So I'll just write that to represent a positive number. Now we see that it actually doesn't really make a difference, because whatever the number is, I'm multiplying by 0. Okay, minus f at c is some positive number, okay, because we know that f is always positive, times, well, g prime at c, I'm working with the assumption that the derivative is equal to 0, it's just going to be equal to 0, all over, okay, g at c squared. Now, what's important here is there would be an issue if g at c were equal to 0, But of course, g at c is not equal to 0 because it's strictly positive. And look what we have in the numerator. The numerator is just 0 minus 0. That's just equal to 0. Okay, and I'm going to say here, since g at c can't be equal to 0. Okay, meaning we know that this fraction has to be equal to 0 because the numerator is 0 and the derivative is definitely not equal to 0. Okay, so if both of the derivatives exist here, in other words, they're equal to 0, we have that h prime at c is equal to 0. Okay, or if either f prime at c or g prime at c do not exist, well, when I try to input it into this equation here, it means that h prime at c will not exist because I'm trying to calculate this expression with something, with one of the terms that doesn't exist. Okay, so we can say then h prime at c does not exist. Okay, so we've just proven the first step here. Okay, so part 1 is proved. Okay, we have shown that given the information that we have, h prime at c has to either be equal to 0 or will not exist. Okay, so the next thing we have to do is we have to determine whether the sign of the derivative changes from positive to negative. All right, so here, and we'll call this part 1, part 2. Okay, so what I need to do is I need to consider h prime, and here I've got my c, and let's start with the left-hand side. Let's pick some number just a little less than c, okay, like we had in these two scenarios. Okay, so if I have h prime at a, let's see what happens. All right, so f prime at a, okay, that first term we know has to be positive because f prime is positive there because f has a local maximum there. Okay, and what do we know about g? Well, g has to be some number greater than 0. Okay, so it's going to be positive. Then I'm subtracting, okay, f at a. So we know f at a, again, like all terms of f, has to be positive. Okay, and then g prime at a, well, remember, g prime at a has to be negative. Okay, and then again, the denominator is just going to be positive because we know g is positive, and so the square is going to be positive. So what do we have? We have a positive number minus a negative number, which just gives us a positive number. Okay, so what we have is that the derivative has to be positive to the left of c. Okay, and now let's do the same thing with h prime at b, some value just to the right of c. Okay, so again, f prime at b has to be negative. G at b, well, g is always positive, so that's going to be positive, minus, okay, f at b, well, definitely has to be positive because they're all positive. And g prime at b, well, that has to be positive. Okay, and again, over g at b squared, which again is positive. So what do we have now? We have a negative number minus a positive number has to give us a negative number. And so we have that h prime at b has to be negative. And so here, there we go. We know that to the right of c, it's going to be negative. But look at what we've done. We've now shown that part 2 of our conditions has been met. So here, part 2 is proved. And so in the end, we can say that h has a local max at c. All right, so let's do a recap here. So step number 1 was to determine what it was that we had to show. And in order for h to have a max at c, the derivative need to be 0 or not exist, and the derivative needs to change from positive to negative. So that's what we had to show. Then we listed what we knew. So we had that f and g were positive values. positive functions for all values, and we knew how the derivative behaved as I crossed the number c. For f, it went from positive to negative. For g, it went from negative to positive. And I used this information to prove that h prime at c had to either be equal to 0 or not exist. And then using my behavior of f prime and g prime in the neighborhood of c, I was able to prove that f had to go from positive to negative. Sorry, h prime had to go from positive to negative, hence proving that we had a local max. All right, that's it for this one.